Okay, next up is a problem I wrote for you to illustrate what to do with an inclined plane. So I have a 20 kilogram block on an inclined plane of 30 degrees above the horizontal. We haven't introduced friction yet, so we're going to assume no friction acts between the block and the plane. And we're going to start by drawing a free body diagram of this block. So I need to draw a dot instead of the block, but I do want to indicate that this is on a tilted plane. So I want to try to draw something that indicates, oops, I probably should be using a ruler for this, but something that indicates that tilted plane. And whenever we have an inclined plane, we almost always, I can think of a case when we don't, consider our x and y axis, our coordinate system, to be along the plane and then perpendicular to the plane, because if an object is constrained to move along an inclined plane, its acceleration, its velocity, everything will be happening, its displacement will be happening along that plane. So we want to have components of forces that are in the direction of that potential change in motion. So we're going to draw a free body diagram for this block. So we know that gravity pulls on the block, but in the flat Earth approximation, of course, gravity pulls straight down. So straight down to the flat surface of the Earth, right? We sort of imagine the ground underneath it. You can also think of it as towards the center of the Earth, as long as we maintain that sort of flat horizon sort of thing. So this is the pull of gravity. And then I know that the plane itself is supporting the box, because otherwise it would be sort of accelerating down towards the flat ground. But the normal force, the support force, is normal, aka perpendicular to the supporting surface. So one of the reasons I draw this dotted line for the plane is that I want to be able to draw that normal force as clearly as I can to be normal to, perpendicular to, that supporting surface. So I'll label that F sub n. You'll notice that I drew, or I hope you'll notice that I drew this normal force to be shorter than the pull of gravity force. And that's because on an inclined plane, the normal force is less than the pull of gravity. And I'll show you that now. So before we move on to number 2, we'll do a quick check. Are there any other forces on the box? Is there anything else touching the box? At this point, no. We're not given any other information about objects in contact with the box, and we're not considering friction yet. So we're done. There's just 2 forces on the block. Now we want to find the pull of gravity on the block and the normal force on the block. So the pull of gravity is straightforward. That pull of gravity is still the mass times acceleration due to gravity. So 20 kilograms times 9.8 meters per second squared. Okay, and I'm not going to even try to think about it because it's Friday and I'm exhausted. So 196 newtons. So that gives us the length, the strength of this downward vector. Now we want to know what's the component of that vector that's directed along the normal to the plane. So this is where we have to do some geometry. In order to decompose this downward pull of gravity, I need to know how the pull of gravity, how that force is related to my new axes. This is essentially y in the normal direction. And it's kind of backwards, but I would choose positive x, if I'm going to label them x and y, as down the plane, because I know that the acceleration of this block, if we allow it to accelerate, will be down the plane. But this is arbitrary. You can keep up the plane to be positive if that's comfortable for you. So now a little argument for how to find that angle. We know that the angle of inclination, we're told that the angle of inclination is 30 degrees. So there's 30 degrees. And so now I kind of extend this line to my straight down pull of gravity. Gravity is straight down. This line is horizontal by definition, right? It's the angle between the incline and horizontal. So these 2 lines must make a right angle. So I have a right angle and 30 degrees. That means this top angle must be 90 minus 30 degrees, or 60 in this case. And then this angle itself is a right angle. So that means if this is 60, this must be 30. So I'll only show this once or twice, but it's always the case that the angle of inclination from horizontal is the same as the angle from the vertical pull of gravity to our new y-axis, or our new negative y-axis. That will always be the case. It's a similar triangles argument. So we now have our angle, and we want to find the the normal force on the block. I need some more colors. So I know that, or I expect that the block is going to stay on the plane. I have to assume that the block will stay on the plane, or else I'm stuck. So in my new coordinate system, and sometimes it's helpful to sort of think sideways, right? This is how we're used to thinking. I would warn you to not do this too often, because you need to remember that the pull of gravity is straight down. This direction is straight down. But in terms of seeing this as a vector decomposition that looks more like what we've done in the past, we have this vector that's now down and to the left, and I want to decompose it into its component that is straight down, right, plus its component that is to the left. So it's a very strange way of looking at the world, and it takes some careful kind of thinking of the first few times, the first maybe 100 times, but this is what we're doing. So we have the component of the pull of gravity that's into the plane, that's in balance with the normal force. So I'm going to label this blue component Fn perpendicular. Oof, that's some funny notation, but maybe I'll stick with it and we'll get used to it. So when I mean perpendicular to, I'm talking about perpendicular to the plane. And then this is F. Oh, it shouldn't be N, it should be G. Fg perpendicular and Fg parallel. Parallel to the plane, okay? Again, the point is, I don't want to talk about this pull of gravity that's straight down. I want to talk about the component of gravity that is now in my negative y direction versus the component of gravity that is in my now positive x direction. And again, this is how we're more used to seeing that right triangle. So thinking about this right triangle, I can say that, so this is what we know to be 196 newtons. If this is starting to get too messy, and maybe it is, we can redraw it. But I know that the pull of, or I should maybe, yeah, no, we'll do it this way. So the pull of gravity in the perpendicular direction is the side of the triangle that's adjacent to this angle. So that component must be equal to Fg times cosine of theta. And then the component of the pull of gravity that is parallel to the plane, this side of the triangle, is opposite to 30 degrees. So that's equal to Fg times sine of theta. And then I'll come back this direction. I'm not sure if that helped. You might be getting sick. But in any case, here we go. So we know that the pull of gravity in total is 196 newtons. And our angle here is 30 degrees. 196 sine of 30. And again, I know the sine and cosine of 30, but I just don't even trust my brain right now. You can see the weirdness of the trig on my calculator. Okay, so this is 169.7 newtons. Running out of room here. Oh, that means this one's half. But don't trust my brain right now. 98. Okay, so again, pull of gravity straight down. But straight down is kind of wonky to our new tilted axes. So I want to decompose this straight down vector into the plane, or perpendicular component, and into its parallel to the plane, or down the plane component. And so I've just done that in our usual manner. So the normal force, Fn, must be in balance with the perpendicular component of the pull of gravity, because we expect it to not accelerate in this direction. So Fn is equal to 169.7 newtons. I'm about to run out of time, so we'll have to continue this in the next video.